Dear students, welcome to my YouTube channel PCM Academy, and let us continue our discussion on postulates of quantum mechanics. So we have already discussed 3 postulates, and in this class we will discuss postulates 4 and postulates 5. So we will be covered postulates of quantum mechanics in this video. So if you are new in this channel, then go to the playlist and see the videos one by one, so that your understanding may be more better. Okay. And obviously, if you are new, then subscribe my channel and hit the bell icon also, so that you will get notifications. Okay. So today we will discuss postulates 4. So what we will discuss in postulates 4 basically, this is the probabilistic outcome of the measurement. Okay. So we know in quantum mechanics, for any physical quantity can be represented by an operator that is known as observable in quantum mechanics. Okay, so the measurement of any observable corresponding to a state vector. So what will be the probability of the measurement of that state, that we will discuss here in postulates 4. This is actually the probabilistic outcome of the measurement of an observable corresponding to a particular eigenstate, you can say. Okay, so let me tell you about that thing. So what we will discuss here, actually the probabilistic outcome. Okay, now suppose we have an observable A corresponding to A, the Hermitian operator A cap, and this A cap operate on a state vector psi. So A cap will be measured, or A will be measured on a state psi, that is, you can say psi of t. Okay, now as A cap is Hermitian operator, we already told that psi can be written as the linear combination of the various eigenstate. Okay, and that will be just simply C1 psi 1 plus C2 psi 2 dot Cn psi n. Okay, where psi 1, psi 2, psi 3 and psi n are the eigenstates corresponding to the observable, or you can say corresponding to the Hermitian operator A cap. Okay, so this will form a complete basis, Now, suppose that the eigenvalue corresponding to psi 1 is A1 and eigenvalue corresponding to psi 2 is A2. Similarly, the eigenvalue corresponding to psi n is An. Now, what will be the probability of measurement An when we will operate A cap on psi t? So what will be the probabilistic outcome of An in the state psi n? So that will say in postulates 4. Okay, so what will be that probability? Okay, that we are going to write. So the probability of finding An, so that is, you can write as Pan. Okay, so this is actually psi n with psi, okay, and mod square divided by psi with psi. Okay, so this is actually the probabilistic outcome. So this psi with psi is the dot product. Actually, this is actually the dot product, or you can say the scalar product of psi with itself. Okay, so this formula you have to remember. Okay, so this is the probability of finding An in the state psi, or in the state psi n, you can say. Okay, similarly, if you talk about any, this is actually general notation for psi n, but you can write it for A1, A2, A3, whatever you can. Okay, so the probability of the measurement of the eigenvalue An, that is the actually corresponding to the observable A. Okay, so that will be actually Pan, and that is psi n psi mod square divided by psi psi. Okay, now we can find that this is nothing but actually Cn square, you can say mod Cn square. We can prove it. This is nothing but the mod Cn square. So how we can write it, that actually I have told earlier calculated earlier that psi n with psi, if you take the dot product of psi n with psi, or scalar product psi n with psi, that will give you Cn by using the orthonormal condition. Okay, so you know, if you take the dot product of psi n with psi, psi means psi of t actually, then what you will get? You will get psi n with psi 1. Okay, so that means C1 star you can say. Okay, so psi n with psi, so that all the terms something like psi 1, psi 2, psi 3. So let me write it again. Okay, so it will be just C1 and then psi n with psi 1, similarly plus C2 and psi n with psi 2 dot dot, you know, that will be Cn and psi n with psi n. Now you know this all values are 0 because the value exists only when I is equal to j. You know the orthonormal condition I have told earlier. So let me tell you again, that is psi I with psi j will actually be delta ij. Now, so delta ij will be 0 if I not equal to j, and will be 1 if I equal to j. So this all term will be 0 except this term. This psi n with psi n will be 1. So it will be just Cn with psi n with psi will be just Cn. Okay, now if you write here, okay, so what you will get? You will get just P of an is equal to nothing but Cn square, or you can write Cn is equal to sin psi, and if you want to write that what will be the normalized by using the normalized condition, you know. So what will be the normalized by using the normalized condition? Normalization Cn will be just psi n with psi, and norm of this, you know what is the norm of this? This is the square root of psi with psi. So I have told this thing earlier in the mathematical tools. So if you are new, please see the videos serially, that you can understand better. Okay, so this is Cn. Now you know what is Cn square, you can say that is Pan. So if you take Cn square, so that will be just psi n with psi mod square divided by psi with psi, and that is basically P of an. So this thing is simply just the coefficient square of the eigenstate. Okay, so if you want to know the probabilistic outcome or the probability of finding the value in the state psi n, then this is just nothing but the square of the coefficient of that psi n, and if this is complex, then obviously this is psi star psi, that means mod psi square. Since Cn star Cn, that is mod Cn square. So if this is this coefficient is complex number, then it will be mod Cn square. Okay, that means Cn star simply, or otherwise it is just the square of this. Okay, or you can find out by using this equation P of n. Okay, so this is, but here this is actually the an, the value of an is non-degenerate. Okay, that means an can be find out, or an can be get only for the eigenstate psi n. But if this is a repeated eigenvalue, if the eigenvalue is same for different, if the eigenvalue is same for different eigenstate, then this is called degenerate eigenstate. So in that case, what will be the probability? Because you know, when you want to find out P of an, so you will get an only for the eigenvector psi n. So an is the eigenvalue only for psi n. But if this is the repeated eigenvalue, that if this is for psi n also, this is for psi 2 also, psi 1 also, then we have to take the probability for each and every eigenvalue, and we have to add this, because probability, you know, the addition property of probability. So you have to add this. So this is true only for non-degenerate eigenvalue. Okay, so this is true only for, you can write here, this is true only for non-degenerate eigenvalue, but for talk about for a degenerate eigenvalue. For degenerate eigenvalue, what will be this expression? And suppose it is m times degenerate, m degenerate. Okay, so if you take the eigenvalue equation, that is for psi 1, suppose, so a cap psi 1, suppose. Okay, so for psi 1, suppose this is psi n, suppose. Okay, so let me write in this way, that psi n 1, okay, in general. So that will be, suppose, n psi n 1. Okay, so for this eigenstate psi n 1, you can see the eigenvalue is n. Similarly, if psi n 2 and the eigenvalue is n again, so in that case you can see that n is the degenerate, 2 times degenerate. But in the same way, if we write psi n m, as you here write that this is m degenerate, so that will be equal to same, that is psi n m, this kinds of thing. So if this is happening, then what you have to take? You have to take the probability of each and everything, of each and every state. So in that case, what will be your total probability? So the total probability P n of a n, okay, so that is just for the first state psi 1, what will be your probability getting a1? If you take the measurement for the state psi n1, then what you will have? You will have psi n1 psi mod square divided by psi with psi. So you will get this. And for this state, you will get psi n2 with psi mod square divided by psi with psi plus dot dot, you will get the last term, that is psi nm psi mod square psi with psi. Okay, so you can write this as summation form, that will be j is equal to, suppose, 1 to m psi n m psi mod square and psi with psi. So this is your total probability, you can say. Okay, so we have to use the rules of addition of probability simply. So for m degenerate eigenvalue, your probability will be this, but for non-degenerate eigenvalue, so your probability will be this. Okay, so this is how you can find out the probability for a discrete spectra actually. So you know here a1, a2 and a3, an are the discrete value. But if this is continuous value, so in that case, if the spectra is continuous spectra, in that case the formula will be something different. Okay, so this is also valid for discrete spectra. Now for continuous spectra, what will be your probability? Okay, so for continuous spectra, what will be the probability? So in that case, we will say the probability of finding a value between a to a plus dA, suppose a to a plus dA. So what will be the probability density? That means dPA upon dA. So that will be the probability density. So that is the actually the measurement of a, the probability of measurement of a give a value between a to a plus dA, and in that case the probability density dPA upon dA is nothing but mod psi a square divided by psi with psi. Okay, but if you write in general that between x to x plus dx, between x to x plus dx, so that will be just dpx upon dx, that is simply psi of x mod square divided by psi with psi. So our dpx will be psi of x mod square divided by psi with psi into dx. So what will be the total probability? We have to take integration, that means p of x is nothing but integration. You can write it as minus infinity to plus infinity, or in the region that is x1 to x2 you can write in what region you need. So that will be psi of x mod square dx divided by psi with psi. So this is the final result for continuous spectra. This is the total probability. Okay, so this is how you can find out the probability of finding the any value in a particular region or in a particular range for continuous spectra. And for discrete spectra we have different value. There is a discrete value and we have to take the summation of this. So instead of summation we have used here integration actually. So this summation is actually converted into integration, and that is nothing but mod psi x square, okay, into dx. So this is the integration divided by psi with psi. So this is what I have written for continuous spectra. So this is all about the postulates number 4. Now what will be the postulates 5? So postulates 5 is simply, let me write it again. Now there is postulate 5. So postulate 5 give you simply the how the state vector psi of t evolves with time. So time evolution, you can say. What we will say in the postulates 5 is actually the time evolution of psi of t, of psi of 2. So how with respect to time this state vector psi of t will change, and that is given by the time dependent Schrodinger equation. Time dependent Schrodinger equation, that is nothing but IH cross del psi of t del t is equal to h psi of t. So this is actually the time dependent Schrodinger equation. Okay, and here h cap is the Hamiltonian operator, that is nothing but the total energy. Okay, Hamiltonian operator is nothing but the total energy, and this equation is actually equivalent to Newton's second law in classical mechanics. Okay, as in the classical mechanics, Newton's equations show how the position vector r function of t, how the position vector r function of t evolves with time, and that is given by mass into d2r by dt2 is equal to just force. So this equation will give you how this position vector r will evolve with time, and this equation will give you how the state vector psi of t evolve with time, because here the state is defined with the state vector psi, here the state is defined with the initial position and momentum. Okay, so this is how the postulates 5 comes, and postulates 5 tell you how the system will evolve with time. And as I have told you that what is our purpose at the beginning of the postulates of quantum mechanics. If you see the video, you can see I have told you that there are certain steps to study a system. Maybe it's a quantum system, or maybe it's a mechanical system, classical mechanical system. So our first step was to define the state at time t is equal to 0. Then we will see that how that will be first at initially first step 1 was you have to define the state of the system. And in quantum mechanics, state of the system is defined by psi of t, and in classical mechanics it is, you can say, position and momentum. And the second step, that is the statics of the system, we have to know, and that is at t is equal to 0, what is the position and momentum in classical mechanics, and at t is equal to 0, what will be the state vector in quantum mechanics. And then the third part, that is the dynamics of the system, that will expressed, or that will be studied by a certain law that will be the law of this motion, law of this system actually, and that is Newton's law in classical mechanics and Schrodinger wave equation in quantum mechanics. So this is actually the dynamics of the system. So these postulates 5 give you the dynamics of the system. Okay, so this is how we can analyze these postulates, 5 postulates, and this will be very helpful in various applications in quantum mechanics. We will see later on in upcoming videos the various applications of the quantum mechanics. Okay, so this is the end of the postulates of quantum mechanics, and we will discuss next thing in the next class. Okay.